Hi, I'm just going over a couple of notes that I read out a couple of days ago. Let me have a look at these. I don't know if these ideas made it to the web or not. Let me just go over this again. Can we build a speech recognizer based on the storage of the exact waveform? So my thinking was that there have been some suggestions that there are 10 to the 15 synapses in the brain. If that's the case, we could store 10 to the 6 bits per second for 10 to the 9 seconds, which is more or less our waking hours, 10 to the 9 seconds. We could store 10 to the 6 bits a second. This is assuming that there's one bit per synapse. Don't know whether that estimate is too big or too small. So I'm just wondering if by storing actual waveforms in the brain, that this actually provides us with a method or a strategy for developing a speech recognizer. The reason that I say that it might offer a design method for a speech recognizer is the fact that we can apply a cost. We can make it expensive to store and retrieve things, and given those cost factors, the method that we come up with may be optimal. So first of all, imagine that we've got some waveform stored in the brain, and we're given another sample and we're asked to search for a piece of that waveform. Okay, look, I'll just assume first of all that we have somehow we have exactly the same bits. We're given a piece of waveform, we're asked to match that, find that in the signal, and it's inconceivable that that actual waveform would be in the signal unless the thing that we're matching against was actually snipped out of the actual digital signal. The odds against it would be inconceivable unless it was a flat line or something. But let's have a look at this case a bit more carefully. We want to find a waveform by searching. We're given a little piece of it as a key, and when we search our database for that waveform. We could search it linearly, as the term some people use. We could search it from the beginning to the end, the database of billions of bytes, and we can find a little piece of waveform, be it 3 bytes long or 300 bytes long, doesn't matter. But let's assume that it's just a little waveform, a little piece. Maybe it's just 3 or 4 bytes long. We're matching that against our database of billions of bytes. Okay, now let's make it expensive to do that searching. Let's make it incredibly expensive so that we can't afford to look through the database of billions of the bytes sequentially. So we've got to find another way of storing our waveform. And how exactly we're going to do that, I don't know. But this is a question that's raised, just the fact that we put that constraint on it. Presumably it's going to immediately mean one thing. If there's a cost for searching, we may want to store our stuff in some kind of binary tree format. And I think there's another consequence of this cost. I think it also may be effective to get inexact matches. All I'm thinking is here that given this vast quantity of data that we've got to index in some way, it may be very useful at some point in that index to have inexact matches, so we're not matching on the full well, let's say it's a 16-byte signal. 16-bit signal. We're not matching on that 16-bit signal in its entirety. Maybe data that's been reduced from that may have a maybe only 1 or 2 decimal places. In order to proceed, we think about working the exact waveform to a specified bit rate. But what I'm hoping is that this strategy will lead to a more general solution. So we assume there's a cost to searching and there's a payoff if you find the right item. If there's a payoff for the right item, this gives a very strong incentive to using partial searching methods. So how can we make such a system work? At the moment I have no idea. I'm just offering this as something to look at.